There are a couple additional MOSFET configurations that we want to consider. The first is that if we have MOSFETs on an integrated circuit or an IC, they're typically going to be biased with a constant current source as opposed to that voltage divider resistor biasing that we saw in the previous few videos. And so there's a couple main reasons why that is. The first reason is that using that constant current source means that our Q point is going to be more stable. So Q point will be more stable. And the second point, which is also very important, is that our current source can actually be made of mostly MOSFETs as well. So current source can be made with mostly MOSFETs. So we can just use more transistors to bias that first transistor. And so the main reason we would want to do that is because, remember, our transistors are in general going to be much smaller than our resistors. So smaller than resistors. So anytime that we can replace a resistor with a transistor, that means we're able to fit more things on a given space, which ultimately translates to more processing power, more memory, whatever the application may be, we're able to do more of it in a given chip. So that's usually desirable. And so we're going to come back to this second point, and we're going to look at how we can do that with how we can construct various types of current sources with our MOSFETs in our applied electronics class in a future semester. So the other main configuration that we can see is something called a diode type configuration. And so in this case, our MOSFETs are being used in place of resistors. So MOSFETs can be used in place of our resistors. So this goes back to that same size advantage if we're talking about integrated circuits in particular. So we can replace resistors with something much smaller. And so again, as I mentioned, they're going to be connected in what's called a diode type configuration. So we'll see why here in a minute. So diode type configuration. And so in this configuration, our drain and gate terminals are connected together. So let's sort of just draw that out real quick. So here we have our drain, here we have our source, and let's say our source is at ground, and we have some voltage VDD. And so we're just going to take this gate terminal and we're going to connect it directly to our drain. So our voltages of interest are, of course, this VDS and our VGS here. And so what we can see is that our VDS is equal to our VGS in this case. And so remember, our VDS sat is equal to VGS minus VTN. So that means that our drain voltage, VDS, is always going to be greater than our VDS sat. So again, let me just write that out. This is equal to VGS minus VTN for our NMOS transistor that we're considering here. Of course, a similar case for our Pmos. And so what this means is that, again, the device is always in saturation mode. Well, so long as it's not cut off. So it can also be cut off, but if it's turned on, it's always going to be in saturation. So in that case, we can say that our ID is equal to Kn times VGS minus VTN squared. And because our VGS is equal to VDS, we can also write this as Kn times VDS minus VTN squared. And so ultimately what we have then is something that behaves like a nonlinear resistor. So we would call this an enhancement load device. So enhancement load device. So again, it's behaving like a non-linear resistor, or essentially like a diode. So if we were to briefly sketch our IV curve, we would see something like this. So here is our ID, and let's plot that versus our VDS. So this is our VDS. And so we're going to have some critical point on our VDS axis, which is going to be our threshold voltage. So we still have to exceed that threshold voltage because, again, our VDS is equal to VGS, so of course that has to be above the threshold. But once we're above that threshold, we get a curve that looks much like a diode curve based on the equation that we had above. And so let's see if I can draw that a little bit better. And so that's just based on this equation up here. And so again, the main sort of appeal of doing that is we can replace resistors and have something much smaller in our circuits, particularly in integrated circuits. So there are other configurations that we can consider as well. And if you want to see an example of this being used in a circuit, you can look on page 158 in the textbook.